There is this feeling right now in the tech world. It's it's a bit like the gold rush.
Mm.
Everyone is grabbing a shovel. Everyone is sprinting toward the mine, screaming, Eureka.
Right.
But nobody seems to have stopped to ask if the mine shaft has supports or, if there's actually enough oxygen down there.
Eh.
We are just digging.
That is a terrifyingly accurate metaphor. And I mean, usually in mature industries like construction or aviation or even food safety, you have these massive books of regulations, the rules.
Exactly.
But in AI, it really does feel like the Wild West.
Well, that's exactly why I pulled this document for today's deep dive. Because it turns out there are rules, or at least a very serious, very global attempt to write them down. We're looking at ISO IEC 23894.2024.
The 2024 edition. Okay, so this is fresh off the press.
It is brand new, and specifically, we are ignoring the boring bureaucratic stuff in the front. Sorry to all the compliance officers listening, and we are skipping straight to Annex A.
Annex A. It sounds like a secret government file or something.
It kind of does.
Yeah.
But the premise today is a little different. We aren't just summarizing. We're sort of stepping into the role of instructors.
Okay, I like that.
Imagine we're running a seminar for people who actually have to build this stuff or buy this stuff, and we are going to treat Annex A as the curriculum.
I think that approach works really well because Annex A it's unique in this document. The rest of the ISO standard is about process, how to hold a meeting, how to file a report, how to structure your org chart, all that stuff.
Right, the how.
The how. But Annex A is about substance. It essentially asks, what does a safe or a good AI system actually look like? What are the concrete objectives?
Right. And looking at this list, we have, 12 distinct objectives here? It strikes me that this isn't just for coders. This reads like a cheat sheet for a CEO or a product manager or, frankly, a lawyer who is trying not to get sued.
Or a regular person trying to understand why their bank loan got denied by a robot.
Exactly. So our mission today is to walk through this curriculum. We're going to tackle these 12 objectives from 8.1 to 8.12 in order. By the end of this, we want you to have a really comprehensive mental checklist.
Think of it as building a lens. That's how I see it. If you don't know what you're looking for, you won't see the risk. These 12 objectives are the lens through which you can spot the dangers before they happen.
I love that. Okay, class is in session. Let's open the textbook, section A.1, general.
So A1, it just sets the stage. It basically says, here is a list of objectives regarding AI risk. But there is a crucial nuance right off the bat that I think a lot of people miss.
Okay.
The standard says that when identifying risks, you have to look at AI-related objectives. But, and this is the key, it depends on the nature of the system and the context of its application.
Okay, hang on. That sounds a little bit like a loophole. It depends on context. Does that mean I can just say, well, my context, safety doesn't matter?
Yeah, nice try. But no, it's not a get-out-of-jail-free card. It's more of a focus-your-attention card. The standard is explicitly saying context is king.
Right.
You cannot treat every AI system as if it's controlling a nuclear arsenal.
So if I'm building a chatbot to recommend pizza toppings, my risk profile is?
Virtually zero regarding physical safety. You don't need to worry about the pizza bot exploding.
Okay, good to know.
But maybe you have some privacy risk if you're collecting addresses. Contrast that with building an AI to triage patients in an emergency room. The risk objectives change completely. The standard says you have to identify which of these objectives matter before you even start building.
But 8.1 also says this list 8 and 2 to 8.12, call it the foundational list. It's the baseline.
It is the baseline.
Yeah.
Right. It's not exhaustive. You might have other risks specific to your industry or whatever, but these are the ones you must consider.
You have to start here.
You have to start here. And here is the instructional note I want to highlight for everyone listening. These objectives act as that lens we mentioned. If you, as an organization, simply don't care about, say, environmental impact,
You're just not going to see it.
you literally won't spot the risk associated with it. It's not even on your radar.
It's like cognitive blindness.
Exactly. The standard is forcing you to put these objectives on the table so that the risks become visible. You have to prove you looked through the lens, even if you ultimately decided there was nothing there to see for your specific use case.
Okay, so we have our glasses on. We are ready to see the risks. Let's move to the first major pillar, section 8.2, accountability.
This is a big one, and it's a word we throw around a lot in tech. We need accountability. We need responsible AI. But, I mean, usually when a company says that, it just means we have a PR team to write an apology if things go wrong.
Yeah, right. We take full responsibility for the glitch that deleted your life savings.
Exactly. But the standard actually breaks this down into two very weirdly specific types. You have organizational accountability, and then you have system accountability.
Let's peel those apart. Organizational seems straightforward enough. The company is the boss, right?
Ideally, yes. Organizational accountability is the buck stops here principle. It means the entity, the corporation, the hospital, the government agency, whatever it is answerable for the decisions and actions of the system.
Okay, but play devil's advocate with me here.
Mm-hmm.
In the old world, if an employee messes up, let's say a bank teller steals money, you blame the teller. Maybe you fire them. You hold them accountable. If an AI messes up, you can't fire the algorithm. So who do you blame?
And that is exactly why the text flags this as a unique risk. It calls it a shift in the accountability framework. We are moving from a world where persons perform actions to a world where systems perform actions. This creates a vacuum.
A responsibility vacuum.
That's the perfect term for it, exactly. Imagine a self-driving car hits a pedestrian. In the old days, the driver's accountable. They were texting, they were distracted, whatever.
Sure.
Now, the car was driving itself. Who is accountable?
The manufacturer.
Maybe. Or maybe the person who provided the training data for the vision system, or the city for painting the road lines wrong, or the passenger for not hitting the emergency brake in time.
So everyone just points fingers at each other.
The standard warns that without clear organizational accountability, everyone points the finger at everyone else, and the blame gets diluted until it basically disappears.
And nothing changes.
Nothing changes. And there is a regulatory angle here, too, that's really important. The standard mentions that developers and users need to be aware of legislation in the countries where the system is brought to market.
Oh, right.
If you are deploying a medical AI in Europe, the accountability framework, the laws, are wildly different than in the US or in Asia. You have to know the rules of the road before you even start driving.
Okay, so that's the legal side, the big picture. But then we have the second type, system accountability. This one sounded more sci-fi to me when I read it.
It sounds like it, but it's less sci-fi and more forensics. System accountability is about traceability. Can you prove, technically, with logs and data, that this specific system made that specific decision at that specific time?
Wait, isn't that obvious? The computer did it. Why wouldn't we know?
You'd be surprised. In complex modern systems, you might have 20 different AI models all talking to each other in real time. One identifies the image, another processes the language, a third decides the action.
Ah, okay. A whole ecosystem.
It's a whole ecosystem. If the car crashes, system accountability means you can trace the signal back through that whole web and say, aha, it was the vision module at 12:01 p.m. running version 4.2 that mistook the stop sign for a speed limit sign.
I see. So organizational is who goes to jail, and system is how do we prove what actually happened?
Spot on. And here is the kicker. The standard implies that for many modern black box AI systems, we actually don't have system accountability.
We don't.
We don't know which part of the neural net triggered the decision. It's just a bunch of math. We can't point to the one neuron and say that one did it.
And if you don't have system accountability,
Then you can't really enforce organizational accountability. You can't blame the company if you can't prove their software did it. It becomes a perfect crime.
that is deeply unsettling. Okay, let's move on before I get too depressed. We know we need to be accountable, but to build these things, you need skills, which leads us directly to section 8.3, AI expertise.
Right. And this one seems obvious, doesn't it? You need to know what you're doing.
It does. Why is it a risk objective? Why isn't it just a hiring requirement?
Because the argument the source makes is that AI systems are fundamentally different from non-AI software solutions. They're not just another program.
How so?
If you try to treat an AI project like a standard IT rollout, just, installing Microsoft Word or updating a server, you are introducing massive, massive risk.
So you can't just use your standard IT staff.
Not without significant upskilling. The text emphasizes that organizations need a selection of dedicated specialists. And it's not just coders. It says interdisciplinary skill sets.
Interdisciplinary.
Yeah, you need people who can assess, develop, and deploy. So that's the tech side, the ethics side, the project management side.
It sounds like they are asking for unicorns.
Yeah,
People who know code, ethics, statistics, and law all at once.
they kind of are. But here's the part that really stood out to me in the text, and I want to make sure our students today really hear this. Expertise shouldn't stop at the developers,
It talks about the users.
the end users. This is the crucial detail. This is where so many projects fail.
I read that part and I scratched my head. I mean, do I really need a degree in machine learning just to use ChatGPT? That seems like a really high bar.
You don't need to know how to code it. But the text says users need sufficient understanding of how the system functions.
Okay.
And here is the aha moment. The text says users need to be empowered to detect and override erroneous decisions or outputs.
Override. That is a powerful word. That's not just use.
It is the safety valve. It's the big red button. If the user doesn't have a baseline of AI expertise, they will fall into what we call automation bias.
Break that down for us. What's automation bias?
Automation bias is the psychological tendency to trust a glowing screen over your own gut instinct. It's that feeling that the computer must be smarter than you.
Right. The computer must know something I don't.
Exactly. So if the computer says, deny this loan or turn the steering wheel left, an unskilled user will just do it. They'll just obey. They assume the machine knows best.
But an expert user would be more skeptical.
An expert user, someone who understands that AI hallucinates, that it has biases, that it makes mistakes, will say, wait a minute, that doesn't look right, and hit the override button. They question it.
So the risk isn't just that the machine is wrong. The risk is that the human doesn't know when the machine is wrong.
Precisely. The standard is effectively saying, if you deploy a powerful tool to people who don't understand its limitations, you have failed the expertise objective.
It's like you gave a chainsaw to a toddler.
And then blame the toddler when they cut down the wrong tree. It's your fault for giving it to them without training.
Okay, let's keep moving down the list. We have the people. We have the accountability framework. Now we need the fuel for the fire, section 8.4. Availability and quality of training and test data.
This is the engine room. And the expert text clarifies that this applies specifically to systems based on ML or machine learning.
Right.
Because in ML, the code isn't the primary driver of behavior, the data is. The algorithm learns from the data.
The deployed system behaves based on the production data.
Exactly. Garbage in, garbage out. It's the oldest rule in computing. But the standard lays out some really specific validation requirements. You can't just dump a bunch of data into a bucket and hope for the best.
What are the specific things we need to look for? What does quality mean here?
Well, first, currency and relevance. Is the data up to date? If you train a stock market AI on data from 1990, it's going to fail spectacularly in 2026.
Because the world is different.
Completely different. And is it relevant to the intended purpose? Is the data you have actually useful for the question you're asking?
That seems straightforward.
It does, but you'd be surprised. Second is features. This one is a bit more technical. The data needs sufficiently diverse features to provide strong predictive power.
What do you mean by features?
Imagine you are trying to predict the price of a house. If your data only includes square footage and number of bedrooms, you are missing crucial features.
Like what?
You are missing neighborhood, school district, year built, proximity to a highway. If the data lacks those features, the AI cannot possibly make a good prediction, no matter how smart the algorithm is. It's flying blind.
Got it. And there was a note about consistency, right? That caught my eye.
Yes, consistency. The text says consistency should be ensured across training and test data.
Why does that matter so much?
It's critical. If your training data is formatted one way, say, dates are written out as day, month, year, and your test data, the data you use to check if it's working, is month, day, year.
The results are going to be junk.
Total garbage. You are measuring noise, not signal. It sounds basic, and it is, but data drift and simple formatting errors kill more AI projects than bad algorithms do. I promise you that.
Now, here's where it gets scary for me. The external problem. The text has a specific warning about what happens when the data isn't yours.
This is a huge issue in modern AI, a massive one. The text explicitly says, it is possible that training and test data is not available in the company and is sourced externally.
So you're buying the data or scraping it from the web.
Exactly. You go to a data broker, and the risk objective here is that data quality must be ensured, even and especially in that case. The standard basically says, I don't care that you bought it from a vendor, it's still your responsibility.
You can't outsource the risk.
You cannot. Think about it like a restaurant. If a chef serves you rotten spinach, they can't turn around and say, well, the farmer sold it to me that way, it's not my fault.
Of course not. The chef is responsible.
The chef is responsible for checking the ingredients. It's the same principle. If the external data is poisoned or biased or just low quality, that is your problem.
And checking external data must be incredibly hard.
It is, because you usually don't see how it was collected. You don't know the process. It's a farm-to-table problem, but for information.
Moving on to section 8.5, environmental impact. This is one that I think often gets overlooked in the rush to build cool tech. We just focus on the software.
It does, and the standard frames this as a double-edged sword, which I think is smart. It acknowledges both the positive and the negative effects.
Okay, let's start with the positive, just to be optimistic for a second.
The text gives a specific example. AI can be used to reduce nitrogen oxide in a gas turbine. So you can use AI to optimize complex systems to be cleaner and more efficient.
That's the green AI promise.
That's the promise, using compute to save physical resources. That's the good side.
But then there is the negative side.
The extensive use of resources. And the text zooms in on one specific phase, the training phase.
Yeah, training these massive models. I've read some of the numbers on this. It's staggering. Training a large language model can have the same carbon footprint as driving a car to the moon and back.
It consumes substantial electrical power and requires massive computing resources. The standard is telling you that environmental impact isn't just about what the robot does physically, like whether a self-driving car leaks oil.
Right.
It's about the carbon footprint of building the brain in the first place.
It's the hidden cost. The cost before the thing even exists.
It is. And as an organization, the standard says you have to weigh that. You have to do the analysis. Is the environmental cost of training this model worth the benefit it provides?
That's a tough question.
It is.
Yeah.
But if you burn a forest worth of carbon to build an AI that writes slightly better marketing limericks, you have failed the environmental impact objective. It's that simple.
It puts it in perspective. It forces a cost-benefit analysis that actually includes the planet.
Exactly. Which it should.
Okay, let's talk about 8.6, fairness. This is a huge topic in the news, and I want to be careful here because fairness can sound political or subjective, but the standard treats it as a technical failure mode.
That is absolutely the right way to view it. It's about system performance. And the standard defines the scope very clearly. This specifically applies to systems for automated decision-making affecting specific persons or groups.
So if my AI is just controlling the temperature in a server room, fairness might not be the primary concern.
Probably not. The server doesn't have rights. But if it's deciding who gets a job or who gets a loan or how long a prison sentence should be, then fairness is paramount.
It's about high-stakes decisions.
High-stakes human decisions. Exactly.
The text lists specific sources of unfair outcomes. It calls them out as the root causes. Let's walk through those mechanisms because I think they're really insightful.
Yeah, this is important. First, it mentions bias in objective functions. This is subtle and really dangerous.
What is an objective function?
It's the goal you give the AI. It's the prime directive, like maximize profit or minimize time.
Right.
If you tell the AI maximize profit, and the most profitable strategy happens to be exploiting a vulnerable group of people, say, by charging them higher interest rates, the AI will do it. Not because it's evil or hates them, but because it loves the goal you gave it.
The bias isn't in the data, it's in the goal itself.
Yes. It's a genie in the bottle problem. You wished for money, and the genie did something terrible to get it for you. You have to be careful what you wish for.
Wow. Okay, what's next on the list of root causes?
Second is imbalanced data sets. This is the one we hear about most often. If your facial recognition data is 95% white men, it won't work well for women of color. It's a basic sampling error.
And third,
human biases in training data. This is different. This is when the data itself reflects past prejudice. If the humans who labeled the data were prejudiced, the AI learns that prejudice.
so if historical hiring data shows that a company never hired women for executive roles,
The AI will learn a simple rule. Women are not executives. It effectively codifies the past bias into the future code. It launders prejudice through math.
and the fourth one mentioned is providing feedback to systems.
Right. This is about how systems evolve. If the users providing feedback, the ones clicking yes or no, are themselves biased, the system will slowly drift towards that bias over time. It learns from its users, for better or worse.
The standard also mentions this life cycle view, which I found interesting.
Yes. It notes that unfairness can be caused by a bias issue in the product concept, problem formulation, or choices about when and where to deploy.
So it's not just a technical bug in the code of the data. It can be a conceptual bug, a failure of imagination at the very beginning.
Exactly. If you choose to deploy a predictive policing system in a neighborhood that has a history of being over-policed, that is a fairness failure, even if the code works perfectly according to its design. The design itself was the problem.
The context of deployment.
The context is everything. The source points to another document, IEC 24027, for a deeper dive on this, but the takeaway here is that you have to look for bias everywhere, from the first whiteboard sketch to the final deployment.
Okay, next up is section 8.7, maintainability. This sounds like standard software stuff. Can we fix it if it breaks? Software maintenance.
It is, but with a major AI twist. This is what I call the black box maintenance problem.
Why is it harder for AI than for, say, a website?
So the expert text defines maintainability as the ability to handle modifications, correct defects, or adjust to new requirements. Standard stuff, but then it drops the hammer. AI systems based on ML are trained and do not follow a rule-based approach.
Right, it's not like a simple if X then Y statement.
Exactly. In traditional plot, if there is a bug, you go to line 400 and you change a plus sign to a minus sign. You find the error, you fix the error, you patch the line of code. It might take 5 minutes.
But in a neural network, how do you patch a neural network?
You can't. In a neural network, the logic is distributed across billions of numeric parameters, all interconnected. You can't just patch a neuron like you can a line of code.
So what do you do if the AI makes a mistake?
You might have to retrain the whole thing, or at least a significant part of it, which is slow, expensive, and unpredictable.
Which goes back to the environmental costs we talk about. Every time you have to fix a bug, you're burning more carbon.
It connects back to everything. And think about the analogy of a brain versus a machine. If a car has a flat tire, you change the tire. That's traditional software.
Cool.
If a human brain has a traumatic memory or a phobia, you can't just reach in with tweezers and pull out that specific neuron.
You have to do therapy. You have to retrain the brain.
You have to do therapy, which in AI terms means fine-tuning with new data. So the consequence, as the text says, is that the maintainability of an AI system should be investigated.
You can't just assume it's fixable.
You cannot assume that your standard maintenance contracts and your usual IT workflows will apply. You might build something that is effectively unfixable without starting from scratch. That is a terrifying thought for a business. Building $1 million system that you can't repair.
All right, let's switch gears. Section 8.8, privacy. Now, we all know about GDPR and data protection. Is this just repeating that, or is there an AI-specific angle here?
It builds on it, but it goes much deeper into the AI specifics. The text defines privacy in the usual way: the ability of individuals to control or influence how their information is collected, stored, and processed. And it links this directly to big data.
Because AI eats data for breakfast.
Right. The more data, the better the model. But the fascinating, and honestly, the scariest part of the text is what it calls the inference risk.
Oh, I read this part. This blew my mind. I had to read it a couple of times.
It should. The text says AI systems can infer sensitive personal data from non-sensitive data.
Can you explain that? Because usually we think anonymization protects us. If I remove the names and the social security numbers from a data set, I'm safe.
That's what we used to think. But it's wrong. Let's say you strip out all the obviously sensitive info, race, gender, political affiliation. You think you are safe.
Okay.
But the AI looks at your safe data, your shopping habits, your zip code, your music likes, the time of day you log in, all these seemingly innocuous data points.
And it connects the dots.
It connects the dots in ways that humans can't see. It finds patterns. It might realize, hey, people who buy this specific brand of vitamin water and listen to this specific indie band and live in this 5-block radius have a 98% probability of being pregnant.
Even if they never told the system they were pregnant.
Never. The AI infers it. It creates a privacy ghost of you, a shadow profile with all the sensitive details filled in. The text warns about modeling personalities for individuals. Even if you never gave the system your political views, it knows them based on your other behaviors.
So access control becomes even more critical than ever.
Yes. The standard says you have to ensure the AI system isn't used to give unwarranted access to its data. And it explicitly links privacy to fundamental human rights. Improper collection or inference impacts freedom of expression and human dignity.
It's not just a compliance box to tick. It's a human rights issue.
That's the argument. It's that serious.
That is heavy. Okay, let's look at the next two together. Section 8.9, robustness, and Section 8.10, safety. Because in my mind, these two are twins. You can't really have one without the other.
I agree. They are twins, but maybe. Fraternal twins. They're related, but they look a little different.
How so?
Robustness is. Can the system take a punch without breaking? Safety is. Does the system accidentally punch me?
I like that. That's a good way to put it. Let's talk about taking a punch first. 8.9, robustness. The standard defines it as the ability of the system to maintain its level of performance under various circumstances.
And the text lists two big circumstances to worry about: invalid inputs and stressful environmental conditions.
Invalid inputs, like typing gibberish into a chatbot.
Or worse, much worse. Think about putting a few small, strategically placed stickers on a stop sign that makes a self-driving car's vision system think it's a 100-mile-per-hour speed limit sign.
That's an invalid input.
That's a malicious invalid input, an adversarial attack. The system needs to be robust enough to say, wait, that doesn't make sense, and not just blindly obey.
And the text mentions neural networks specifically again here. It calls out the neural network challenge.
It does. It says neural network architectures represent a specific challenge because they are hard to explain and they behave in a non-linear nature.
Okay, nonlinear. We hear that word a lot. Translate that for us. Why is nonlinear bad for robustness?
Imagine you're walking up a hill. A linear system is like a smooth, perfectly even ramp. If you take one step forward, you go a predictable amount higher. The input and output are directly related.
Okay, that makes sense. Predictable.
A nonlinear system, like a deep neural network, is like a jagged mountain range with sudden invisible cliffs. You can be walking along a flat part, take one tiny step to the side, change just one pixel in an image, and fall off a 1,000-foot cliff.
So the AI goes from I am 99% sure this is a panda to I am 99% sure this is a school bus.
Just because of one pixel. That is nonlinearity. It means the system is brittle and unpredictable in ways that are hard to test for.
That sounds incredibly unstable.
It can be. That's why the text says characterizing the robustness of neural networks is an open area of research.
That's fancy talk for we don't actually know how to fix this yet.
That is exactly what it means. It's a confession. We are deploying systems that we know can be tricked in these weird, non-linear ways, and we can't fully verify them because the math is just too complex.
Which leads us directly and terrifyingly into Section A10, safety. Because if the system isn't robust, if it thinks the stop sign is a toaster oven, people can get hurt or worse.
Correct. Safety relates to the expectation that the system does not endanger human life, health, property, or the environment. It's about physical, real-world harm.
The text lists the obvious high-stakes domains: automated vehicles, manufacturing devices, robots. But there is a very specific operational detail here that I want to highlight because I think it's often missed. The handover.
The handover from the system to the agent. This is probably the most dangerous 3 seconds in modern AI.
Walk us through that. What is the handover problem?
It refers to a level of automation where an external agent, usually a human, must be ready to take over when the system fails or reaches its limit.
Okay.
The text says this handover can be a major risk source, a huge one.
Because of time constraints or the person not paying attention?
Both. Imagine you are in a self-driving car, but it's one of those level 3 systems. You're reading a book, you're relaxed. The car has been driving perfectly for an hour. Suddenly it beeps loudly and says, "Take over now." Pure panic. You have maybe 1.5 seconds to figure out what is happening, drop your book, orient yourself, grab the wheel, assess the situation, and make a life or death decision.
That sounds like a recipe for disaster. It's impossible.
It is. The attention of the agent is the weak link. If you design a system that relies on a perfect, instant human handover, you are failing the safety objective. The standard forces you to analyze that transition point as its own unique risk.
It feels like the standard is calling out the human-in-the-loop fallacy. Companies love to say, oh, it's safe because a human is watching.
Right.
But the standard is asking, is the human actually watching? Can they actually react in time?
And if the answer is no, then you haven't solved the safety problem. You've just created a new one and given it a fancy name.
Okay, now let's talk about the bad guys. Section A111, security. This is different from safety.
Very different. Safety is about accidental harm. Security is about intentional, malicious harm. This is about protecting the model itself from attack.
The text links to ISO IEC 27005, which is a general information security standard, but it says you have to add the AI context.
Yeah.
So what are the new vectors of attack? How do you hack an AI?
The text lists 3 big ones that are very specific to machine learning. First, data poisoning.
We touched on this a bit with data quality. This is corrupting the training data on purpose.
Exactly. It's malicious. If I can slip some bad data into your training set, I can install a secret backdoor in your AI that only I know how to trigger.
So you could teach the AI that whenever it sees a picture of your face, it should unlock the door.
That's a perfect example. Sneaky.
Very sneaky. What's number 2?
Adversarial attacks. This is tricking the model at the time of inference, not during training. This is the sticker on the stop sign I mentioned. It's an input designed specifically to exploit that nonlinear brittleness and rake the model's logic.
And the 3rd?
Model stealing. This is reverse engineering the proprietary model.
Stealing the brain.
Exactly. Your trained model is your company's secret sauce, your intellectual property. But by querying the AI enough times, just sending it thousands of different inputs and carefully watching the outputs, I can sometimes build a copy of it. I steal your IP without ever hacking your servers.
Wow. So information security risk management must be considered beyond classical information concerns. It's not just about firewalls and passwords anymore.
It's not. It's about protecting the integrity of the learning process itself, from the data to the final model. It's a much bigger attack surface.
We have made it. We are at the final objective. Section A, Quarty 12, transparency and explainability.
The grand finale. And these two words are so often used interchangeably, but the standard does a really good job of separating them, and that separation is really important.
Okay, let's separate them then. First, what is transparency according to the standard?
Transparency refers to the characteristics of an organization operating AI systems. It's about being open about how you use collected data, what measures you have in place to manage all these risks we've been talking about, and helping stakeholders understand the system's general capabilities and limitations.
So transparency is about the process. It's the organization saying, here is how we built it. Here is our governance policy. Here is the user manual.
Yes, it's about the organization being an open book about its operations. Explainability, on the other hand, relates to the ability to rationalize and help humans understand how a specific system outcome has been generated.
So explainability is about the specific decision. It answers the question, why did I get denied for this long?
Exactly. Transparency is the bank saying, we use an AI model to help us make loan decisions. Explainability is the loan officer saying, you were denied because your debt-to-income ratio was 2% higher than our model's threshold for this type of loan.
That is a key distinction. Transparency is macro, about the system. Explainability is micro, about the result.
Precisely. And the goal, according to the text, is to enable stakeholders, customers, regulators, everyone, to assess the development, operation, and use of the system. If you have a black box that no one understands, run by an organization that is totally secretive, you have zero trust. You need both to succeed.
So we have walked through the curriculum.
Yeah.
8.1 through 8.12. Accountability, expertise, data quality, environmental impact, fairness, maintainability, privacy, robustness, safety, security, transparency, and explainability.
It's a comprehensive list. It covers a lot of ground.
It really is. And looking back at it now, all at once, what strikes me is how interconnected they all are. It's not a checklist where you can just check box number 1 and then forget about it and move to box 2.
That is the synthesis. That's the big takeaway. You can't have safety, 8.10, without robustness, 8.9. If your system isn't robust, it can't possibly be safe.
Right.
You can't have fairness, 8 points, without good data quality, A4. If your data is garbage, your fairness is garbage. It's a house of cards.
And there are conflicts, right? It seems like some of these objectives actively fight each other.
Absolutely. That's the hardest part of this in practice. Think about privacy, 8.8 versus data availability, 8.4. To make the model better and more fair data, you need more information. But to protect the user privacy, you want to collect less information.
So they're in direct tension.
Direct tension. Or think about explainability, 8.12 versus robustness, 8.9. Sometimes the most robust, powerful, and accurate models, like these giant, deep neural nets, are the hardest to explain. They're the biggest black boxes.
So you have to choose between a simpler, more explainable model that's less accurate or a more accurate one that nobody can understand.
Exactly. Managing risk isn't about ticking these 12 boxes in isolation. It's not a simple checklist where you get a score of 100%. It's about balancing these complex trade-offs. You have to sit down and decide, how much explainability are we willing to sacrifice for a 5% gain in robustness? How much privacy risk can we tolerate to achieve better fairness outcomes?
That is the art of risk management, I suppose. It's not a science.
That is the job. The standard gives you the ingredients and the recipe book, but you still have to cook the meal. And every meal is different.
Well, I think we have given our listeners plenty to chew on. This has been a true deep dive into the blueprint of AI risk, a really foundational document.
It's always good to go back to the source, to the primary documents.
Absolutely. So until the next deep dive, keep asking the hard questions and maybe, just maybe, read the footnotes and the annexes.
Always read the footnotes. That's where the good stuff is.
Thanks for listening.